Everyone, I hope you're all doing well today. We are going to dive into our next section, 5.5, where we are going to discover something called the average value of a function and how integrals play into that and their connection. So just kind of looking right away, number one, oldie but goodie, you should be able to blow through that question very quickly. And I promise it has everything to do with what we are doing in our lesson today. So let's just kind of start off. If I wanted the average of four numbers, okay, not a surprise here. We know we would add those four numbers up and we would divide by 4. And I'm going to save us a little bit of time. That would give us a value of 27.75. Okay, now why in the world would we start a calculus lesson with a question as simple as find the average? Well, because we're going to look at how do we find the average of all the outputs kind of and along a curve. Okay, so first thing I would like to do over here is I would just like to take a moment to look at a picture of f of x equals x squared, and we are going to be working on the interval 0 to 4. So this isn't going to be perfectly to scale, but I'm sure we can work with it nonetheless. Okay, so if f of x equals x squared, so at 0, we have 0. At 1, I'm going to have 1. At 2, we're at 4. At 3, we're at 9. And at 4, we are up here at 16. And basically, tried and true, we should be getting a nice, oops, not a line. We should be getting the beginning of a parabola. Okay, so once again, not to scale, but over this interval, this should work pretty well with us. Okay, all right. Now, what I'm asking is what is the average on the interval of 0 to 4 of these outputs if I make the change in x 1? Okay, well, if we want the change in x to be 1, then the exact points that I have currently on the screen are the values that I'm talking about adding up. So imagine you're starting at 0 and the change is 1. So ultimately what I'm asking you to do is take f of 1 plus f of 2 plus f of 3 plus f of 4 and divide by 4. And what do we get out? So we're going to have 1 plus 4 plus 9 plus 16 divided by 4. And we're going to end up with 7.5. Okay. Now that's great. This is more of just kind of a review, okay? But what happens if we start making those values, the change in x, get smaller? So, okay, now I want my change in x to be every half. So that means I'm going to increase the number of outputs that we are going to be calculating. So now my first value would be f of 1/2, then f of 1, then f of 1.5, and f of 2, and so forth. Okay, so we can do a lot of these numbers in our head, like f of 1/2. So 1/2 squared, I'm going to have it at 1/4. Then I'm going to have 1 squared, which is 1. Then I'm going to have 1.5 squared. So I like to think of that as 3/2. So a little mental math, 3/2 squared is 9/4. Then 2 squared would give me a 4. Then 2.5, I want to think of it as 5/2. It's going to give me a 25/4. 3 squared is 9. 3.5 squared, we're going to think 7/2, so that's 49/4. And lastly, 4 squared, which gives me 16. Okay, well, now I'm not dividing by 4. If I count up by every half, I now have 8 values. So my average value now just came out to give me 6.375. Okay, now I did that work a little bit before with my calculator just to save me some time, but you are more than welcome to type those values in and find them. Okay, so I've got so far, let's see, 7.5 and 6.375. Okay, just a mental thought here. If I asked you to make the change in x be 0.1, so every 10th, what do you think would happen to our average? Okay, well, I didn't put it on my paper, but if I started asking you for more and more values to calculate, so in other words, making our change in x go closer to 0. Think about it. If my change in x was 0.1, I'd have an output of 0.1, 0.2, at 0.3, at 0.4, at 0.5, at 0.6, at 0.7, and on and on and on. I'd have 40 values by the time it was all said and done. Well, if I have 40 values and I add those together and divide by 40, what do you think is going to happen to this number that we're looking at? Okay. I'm hoping that you're thinking it's going to become more accurate. Our average value, whatever that may be, of all the outputs along here is going to get more and more accurate. So I want us to consider that the closer my change in X becomes, so the smaller the change in X, I should say the closer the outputs become, so the smaller the change in X, means that I'm going to get a more accurate average value that comes out. So let's consider this part C here. Find the average value on 0 to 4 if the change in X goes to 0. So how would we do that? Okay, so this is kind of getting at more of the big picture. Well, I'd have to start calculating outputs, right? Just like I did with the previous problem, the 1/4 plus 1 plus the 9/4 plus 4 plus 24/4 and so forth. So what am I calculating? I'm going to be calculating a whole lot of outputs, right? Starting with, it all depends on what my change in X is. I mean, my goodness, if my change in X is 1/100th, the very first output is going to be f of 1/100th, okay? So if I keep doing that, I'm going to keep on going until I get my last term. Now, anytime we're writing out a sequence, we use n to represent our last term that we're going to plug in. So whatever this last iteration is, whatever the last endpoint, I'm going to have f of that. That's going to be my numerator. And then what would I divide by? Well, in number 2a, I had 4 points that I calculated outputs divided by 4. In part B, I had 8 outputs, so I had to divide by 8. In part C, I have n outputs. So I'm going to need to divide by n. Okay. And whatever that value would be would end up giving me my average overall of all the outputs that I could potentially have that are along this curve. Okay, so where does this value come in? All right, well, we've learned in previous sections before this that delta x can be found by doing the difference between the intervals divided by the number of points or the number of values that we're trying to calculate. So let's do a little bit of algebra change here, okay? If I do a little bit of algebra manipulation, what's going to happen is that n is going to be b minus a over the change in x. Okay, well, I want us to figure out what would happen then in this problem. So I want you to think about the limit on n. So as n, sorry, not, I didn't mean to write that. So as delta x goes to 0, what's n going to? Okay, so think about as this goes closer and closer to 0, then that means n is getting closer and closer to infinity. Well, this should make sense, right? Okay, I want every single point, every output that I could possibly get that's along this curve. Okay, so if I blow this up, how close can I make these? How many points would I possibly have along here? Infinite many points. So let's do a little bit more manipulation now. Now that I know that n is equivalent to b minus a over the change in x, let's substitute that back in over here. So my average is f of x sub 1 plus f of x sub 2 plus f of x sub 3. All of my outputs, I'm adding them all up. And n is b minus a over the change in x. Okay, I'm just making the substitute that I found over here. Okay. All right, so what does this mean? Let's do some more algebra manipulation. Okay, if I'm going to divide by a fraction, so I'm looking at this. If I'm dividing by a fraction, I'm just going to save a little bit of time here. That's the same thing as saying let's multiply by the reciprocal. So multiply by the change in x over b minus a. All right, so now follow me because I'm going to do a little bit more algebra here. Okay, so what do we have going on? I've got 1 over b minus a. All I'm doing is separating this out a little bit. times f of x sub 1 plus f of x sub 2 plus f of x sub 3, on and on and on, f of x sub n times delta x. Okay, well, my dears, we've seen this. Back in pre-calc, if you are adding values, all these values over and over and over again, what we have happening is we have a summation. So we have the summation of f of x sub, I don't know, how many values do we want to say? We can't say n necessarily. Like overall, if we add all these together, we're going to say here's the sum of all the numbers times delta x. And I'm going to say, let's start with k is 1 and let's go up to n. Okay, so if k is 1, I've got f of x sub 1. If k is 2, I have the sum of f of x sub 1 times delta x plus f of x sub 2 times delta x. Okay, now in section 3, we talked about definite integrals. And what I want you all to understand is that what we are looking at here is we have 1 over b minus a times the integral of a to b times f of x dx. This is overall what is happening. Now, you have to remember back to the previous section, and we can talk about this more in class, that a summation, okay, and we looked at this very briefly in the video 3 notes, okay, that the summation here is equivalent to the definite integral of a to b of f of x dx, okay? Now, here's the average value equation that we are going to be looking at in class, okay? Now, I just want to point out, I haven't answered the question yet for part C, but we needed to do this work so that now I can go back and answer part C. The symbol we use for average value is the function that's defined f with a line over it, okay? So I'm going to shrink some of this up just a little bit, okay? And what I want to actually do now is find the answer to question C, okay? So basically, we just did a little proof of how do we get that value, okay? All right. So going with question C, if I want the average value as the change in x goes to 0, then what's going to happen? I have 1 over b minus a. That means 4 minus 0. Okay, so think about it like this. Here's a, here's b. Right? So going back, what is then? A is 0, b is 4. What is my function? It was x squared dx. So I've got 1 over 4, 0 to 4 x squared dx. I can use the fundamental theorem of calculus to help us evaluate this so that I don't have to do a Riemann sum, right? And basically we've got 1/4 times, let's see, I've got 1/3 x cubed, okay, from 0 to 4. So I've got a 1/12 x cubed from 0 to 4. So we've got 4 cubed minus 0 cubed. 4 cubed is 64. 64 divided by 12. I'm getting a 16 over 3. So the average value is approximately 5.3. Actually, exactly 5.3 repeating. Okay. All right. So the next question would be, so what does that mean? Okay. In the big scheme of things, we get an average value of 5.3 repeating. Well, what does it mean? If I could find every single output that makes up this curve, the infinite outputs along this curve, and if I could take all of those infinite outputs on this curve, add them together, and then divide by all those points that I added up, we would get out 5 1/3. Okay. So let's move on. The average value of a function f on an interval AB also has a geometric interpretation. Well, it should have a geometric interpretation because we just used an integral. And we have learned in this chapter that an integral means area, right? So if this means area, then average value better have some sort of geometric connection with area, okay? So let's take this graph and let's graph and do what it's asked us to do. So start off with, let's graph f of x equals x squared on the interval of 0 to 4. Okay, so it's 0, 0. Then at the value 1, we get out 1. At 2, we get out 4. At 3, we get out 9. And at 4, we get out 16. Okay, so just like before, this isn't perfectly to scale, but there's the general idea of what our f of x looks like. Okay. All right, so moving along with this, it's asking us to draw the line that represents f, the average value of f. So keep in mind that the average value of f was 5 1/3. So we're going to have to do the best we can on this. 5 1/3 basically is right along here, okay? So this line is our average value, okay? Now in the next part, next question, we're being asked to look at the resulting rectangle of, and what we mean by this is the rectangle that is being formed by the average value of f and the boundaries of 0 to 4. So what I mean by that, if we take a close look, I want you to look at this rectangle, okay? Now let's pretend that's actually on my line 0. All right. What is the relationship between the average value and the rectangle? Okay, so I just want you to think about, sorry, I have my foot caught of all serious silly things. Okay, what is the average value between, or what is the relationship between the average value and the rectangle? Well, the average value is the height of the rectangle. Right? I mean, if I'm asking you to look at the resulting rectangle, the average value is the height. Okay, so what is the relationship between the area of the rectangle and the bounded region of f? This one gets a little trickier. Okay, so remember this just went from 0 to 4. Okay, so let's just think about what is the area of the rectangle. Okay, so I'm going to switch colors just to keep this straight. Okay, so the area of the rectangle, well, we know the base of it is 4, right? It has a length of 4. The height, we also know, is 5 1/3. So, or 16/3, whatever way you want to write it, I don't care. So overall, we know that the area of the rectangle is 64/3 units squared. Okay. All right, so there's your area of the rectangle, but now look at what it's asking you to compare it to, the bounded region of f. Well, do we know how to find the area of the bounded region of f? So in other words, the area under the curve. Well, we sure do, right? We've done this. So I want to know the area in between 0 and 4 of x squared. Okay, this is our area function. So if I want to look at how to figure this out, I'm going to once again use the fundamental theorem of calculus. So this is going to give me a 1/3 x cubed. I need to evaluate it from 0 to 4. So I've got a 1/3 4 cubed minus 1/3 0 cubed. Okay, guess what? 64/3 square units. Ho, ho, ho. So what this is saying is that the area of the rectangle, okay, is equal to the area under the entire curve. Interesting. So what's happening here is that this region, this area is what? Got to be equal to, this whole area here has to be equal to up here. I could be looking at that a little bit wrong. Hold on. So this area, hold on, there we go. This whole area equals this whole area. Okay. Interesting. So the average value is basically giving you a rectangle in the same interval of 0 to 4 that has the same area as the area, the space bounded by our function f of x and the x-axis on the same interval. Okay, well, let's see if we can actually see that come out. Like, does that get proven here? Okay, so let's go back and look at this definition of our average value. Whoops. Okay, so from a to b of f of x dx. Okay, well, we already know from previous sections that this right here means the area under the curve. Okay, so if what we're finding over here is that the area of the rectangle is equal to the area that's under the curve, well, let's just get that alone then. So with some algebra manipulation, I want to move this to the other side. So I'm going to need to multiply both sides by b minus a. Okay, equals the interval of a to b of f of x dx. Well, isn't this what we just kind of saw? Think about what is the average value in this picture. Wasn't it the height of the rectangle? And what does b minus a give you? Isn't that the length or the width? I guess whatever way we want to call it. I'm going to actually go back and I'm going to call it the length. This is our length of the rectangle. Okay, and we're seeing that that has to be equal to the area bounded by f of x and the x-axis from a to b. There it is. Here's our example of it happening. Here's the actual proof of it happening. So what's the relationship between the area of the rectangle and the bounded region of f? They are equal to each other. So the area of our rectangle, because height times length or width times length, whatever way we can change these words a little bit, here is our area of the rectangle is equal to the area of the bounded by f of x and the x-axis. Okay? So there's the concept, my dears. Now it just comes down to let's practice. Okay? So what I want to make sure that is important as we keep going, and we only have these 4 examples, is that you pay attention to the wording of the questions. Oftentimes I find when I'm doing these problems and the homework problems that it's just the little wording that you've got to pay attention to. So let's look at number 3 to start off. Find the average value. It's pretty clear what they want you to do. So average value for us means that we are just going to practice another example that we just learned about. So the average value means I need 1 over b minus a of the interval of a to b of f of x dx. So let's fill in what we've got. We're still sticking with x squared. I've just changed the interval from 3 to 7, or from 0, 4 to 3 to 7. So I'm definitely working with a different area, if you will. Okay, so we'd have 1 over 7 minus 3, and on the integral of 3 to 7 of x squared dx. So what does that mean? I've got 1/4, and I'm multiplying that by, let's use the fundamental theorem of calculus to evaluate. So 1/3 x cubed from 3 to 7. So I've got 1/12 times, well, 7 cubed minus 3 cubed. Definitely going to want to go to my calculator for this. 7 cubed is 343. 3 cubed is 27. So we are getting 1/12 times 316. So I'm getting a final answer of 79/3. Okay. Let's try that box again. All right. That's it. That's the extent of it. So if I was looking now at my picture, if I had just a geometric look at it really quick. So 3 to 7 means I'm out here and I probably have a pretty steep outputs, right? 7 squared gives me a 49. So I'm going from 9 to 49. Okay. So 79/3, if I wanted to approximate this, it's like 26-ish, somewhere around there. So what you're finding is that somewhere here around 26, there's your average value. Okay. So that average value means if we take every single one of these outputs, added them up, and divided by pretty much infinity, you're going to get a 79/3. Okay. So moving on, let's look at the next one. Given f of x, find the average rate of change on the interval 3 to 7. Okay. I really hope that you're cluing into this and you see average rate of change and you realize it really is that easy. No calculus required here. We're going back to Algebra 1 and having a little bit of a flashback. So why is it here? You need to pay attention to average value versus the words average rate of change. So I've got the 0.39 and I've got the 0.7, 49, and we're just going to do a little average rate of change. So 49/9, 7 minus 3, I've got 40/4, 10. Done. Okay. Just here to be a little bit of a trick, so don't let us trick you. All right, next question. Okay. We have average value again. Okay, let's make sure we pay attention to that, but something changed. Look at that little tiny thing. It's asking you for the average value of the derivative on 3 to 7. So first thing I need to actually do then is find the derivative. If f of x is x squared, then f prime of x is going to give me a 2x. So when I'm asking you for the average value now on 3 to 7, I'm looking for this function. Okay, so that's going to go from 6 to 14. That's great. Okay, so still going to do the same thing. It's just my function has changed. So I have 1/7 minus 3, the interval 3 to 7 of 2x dx. So I have 1/4 times, let's see, what are we going to have there? We're going to have an x squared now, right? Because we're trying to integrate it. We're looking at the antiderivative of 3 to 7. So we have 1/4, 49 minus 9. So I have 1/4 of 40, which is 10. Okay, take a look at this lovely. Does it make sense for the average value, and considering it's linear, to be at 10 if we're going from the value 6 to 14? Okay, that worked out pretty nicely. So that's even one we could verify since it was linear. Okay, and our last question for today. So I'm going to look at this one and I'm going to see average rate of change. And I'm highlighting it because if you're not careful, you're going to try to do crazy stuff and everything, and we don't need to. So we've already found the derivative. It was nice and easy. It was 2x. And now I want the average rate of change on the interval 3 to 7. So we've got 3, 6, and we've got 7, 14. So I'm just looking for a 14 minus 6, 7 minus 3, 8/4, or 2. And oh my goodness, did I actually need to do that work? Think about this. They wanted the average rate of change and the function was linear. We could have said 2 right from the beginning without doing any ounce of work, because if we have a linear function, we should be able to give the average rate of change, right? All right, my dears. So that is it. That is our average value lesson for today. Best of luck on your homework. Please let us know if you have any questions. And I hope you all have a wonderful day. Take care.